In the previous example, we were writing a classification code for a one-dimensional problem by using this kind of a parametric approach based upon Gaussian distribution, right? So it's a one-dimensional thing. So xi is the porosity; it's a scalar, right? But now let's try uh, to solve for a classification problem based upon a vector xi, right? So every sample or every rock sample is gonna have two features associated with it. One is the porosity, and the other one is called the gamma ray, right? And the gamma ray is another whale log. It's another physical parameter or physical property that you can measure, right? It's based upon measuring the radiation that's generated by the radioactive decay of a isotope of the potassium, right? So potassium has different isotopes, and because it's so the radioactive decay of potassium is going to generate radiation, and then that radiation is going to be captured by this gamma ray measurement. And the conventional or um, the, 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 the the conventional technique that's used for classifying or detecting the existence of shale is to look at the gamma ray, right? Because shale is rich in clay, and clay has potassium in it. So usually, if you have high gamma values, it's very likely that the rock can be classified as a shale. Right. So we'll have the porosity and the shale. Every rock sample is going to have two pieces of data associated with it, and we're going to use a different data set. Right. We're going to use a different data set, which is called. Let me see. Where is it? It's going to be called gamma porosity phases random. That's going to be our training data set, and then the testing data set is going to be this particular text file, right? So the first thing we're going to do is still to import some libraries, right? Import numpy as mp, and then import matplotlib.pyplot as plot, right? And then load training data. So training data is going to equal to mp.load.txt gamma porosity phases random.txt, right? If we run this code, okay, let's call it E7. And then we're going to get a table that has 600 rows and 3 columns, right? So if we double click on it, it's going to give us this particular table, right? And we're going to see 3 columns. So how many rows? We have 600 rows, which means we have 600 rock samples, right? And then for each row, we have 3 columns. The first column is going to be the measured gamma value, and then the second column is going to be the measured porosity value, and the third column is going to be the manual classification for that piece of rock, right? It's determined by a human being, right? And then the next thing that we're going to do is still try to actually separate the different data into the 2 categories, the training data into 2 categories, right? We still have a 2-class classification problem. So select training data based on manual classification, right? So GP0 gamma, we're just gonna get the gamma and porosity, the first 2 columns, right? And then 0 just means shale, and so 0 means it's a shale, and then 1 means it's a sandstone, right? So GP0 is gonna equal to training data. It's last column. I'm gonna use -1. Last column, right? Last column equals to 0, and then I'm gonna take the first 2 columns, right? That's gamma and porosity, and then GP1 is gonna equal to training data. Its the last column is gonna equal to sandstone 1, right? And then I'm gonna take the first two columns. So if I run that, I'm gonna get two arrays, right? Each one of them is actually 300. So for this particular training data, the total number of sandstone and the total number of shell are identical, right? 300. Each one of them is 300. Now I have like two column matrix, the gamma and the porosity for shell, that's GP0, right? And then and gamma porosity for sandstone, that's GP1, right? And then the next thing that we have to do is to actually get the maximum likelihood estimates for the different categories, right? But before we do that, let's get the prior first, right? The prior for now, the prior is actually gonna be uniform, right? It's gonna be because each category has just 300 samples, exactly the same number of samples, right? But let's still write the codes just in case that in the future, if the training data doesn't have the same number of samples for the different categories, right? So n0, the total number of samples of shell, it's going to be gp0 dot. We're going to use this shape data member of this array, two-dimensional array. The zeroth element of the shape vector is going to give us the row number, right? That's 300, and n1 is going to be equal to gp1 dot shape 0, right? And then prior 0 is going to equal to n0 divided by n0 plus n1, and then prior 1 is going to equal to n1 divided by n0 plus n1, right? So now if we run it, we should be able to actually get 0.5 for the prior, right, of both sandstone and the shell, right? And now let's get the MLE training, right? Let's get the maximum likelihood estimates, right? In the previous example, xi is a scalar, right? So the averages are going to be a scalar, right? And then the covariance matrix is going to be a scalar, right? But here, xi is actually two vector, so the average is also going to be a two vector, and then the covariance is going to be a 2x2 matrix, right? So what's going to be, how do we actually compute that? The average is still quite easy to compute. GP0 mean is going to equal to, because MP has a mean function that takes a vector. But here we have to be careful about how do we want the average to be evaluated, right? We want to average so GP0 is going to be a 300 row, 2 column matrix, right? So we don't want to average the porosity with the corresponding values for gamma, right? That's not the correct average that we want to get. What we want to get is the average for porosity across all the samples, all the rock samples for shell, right? And then the average of all the gamma values for across all the rock samples of the shell, right? And that means what? That means we have to do this average across different rows, right? Across the different rows instead of across different columns, right? So in order to get the average correct, we have to specify axis equals to 0. So if we do axis equals to 0, then it's going to do a row-wise average, right, instead of a column-wise average. What you're going to end up with is a vector of 2 elements. So GP0 mean is going to be a vector of 2 elements. The first element is going to be the average of the gamma across all the shell samples. And then the second element of the vector is going to be the average porosity across all the samples, all the shell samples, right? And then GP1 mean, the average for the sandstone, is going to be AMP dot mean GP1, then axis equals to 0, right? That's just the mean, right? And then we still have to get the covariance matrix, right? So how do we actually get the covariance matrix, right? So GP0, let's just call it a COV, the covariance matrix. We'll have to use AMP.COV now. That's COV, it's a NumPy covariance matrix calculation. And then all we have to do is to give the matrix, but now we have to actually specify how do we want to calculate the covariance, right? We want the covariance the problem is just like this x equals to 0 problem, except that we want the covariance to be computed for porosity and gamma values, right? So in this case, the covariance, the option for the covariance function is called rho VAR. Rho variance equals to false, right? And then GP1 COV is going to equal to MP.COV GP1 rho VAR equals to false, right? So now if we run this code, so now we're gonna get a covariance matrix that's 2 by 2, right? That's 2 by 2. So this is the autocorrelation of gamma value. This is another autocorrelation for porosity, right? And then these two numbers are the cross covariance terms, right? It's a 2 by 2. So that's the sigma y hat, right? So that's sigma y hat. And then once you got the covariance, we're not done yet here, because this time when we actually compute the posterior, we have to actually use the inverse of the covariance matrices, right? And in the past, we can just divide it by the standard deviation squared because it's a scalar. But here, it's a covariance. We have to explicitly evaluate its inverse. So it's an inverse of a matrix, right? So it's a 2 by 2 matrix, right? We have to get the matrix inverse of this covariance matrix. So let's call it GP0 COV inverse, right? And then we are gonna have to use the NumPy linear algebra .inv. That's the inverse function to get the matrix inverse GP0 COV, right? And then GP1 COV inverse is going to be equal to NP.linealg inverse GP1 COV, right? That's the inverse of the covariances, right? And then another term that we are going to need is actually the determinants. Right. If it's a one-dimensional problem, then it's just the absolute value of the standard deviation, which is already a positive number. So that's quite easy to calculate. But here we have to actually compute the determinant of a 2 by 2 matrix, right? That's the determinant that we have to use here. So how do we actually do that, right? Because NumPy also has a determinant function. So GP0 COV, let's call it DET, is going to equal to NP.linealg dot DET. That's the determinant function, GP0 COV, right? And then GP1 COV DET is going to equal to NP.linealg.DET GP1 COV, right? And that's all the code for training, right? So we have obtained all the maximum likelihood estimates of our presumed Gaussian distribution of the conditional probability, or the likelihood, right? And now we can actually try it out on our testing data, load the testing data. And then testing data is going to equal to np.load txt gamma porosity facies test.txt, right? That's going to be our testing data. Let me just run it to make sure that I got the so testing data is going to have just 100 rows and 3 columns, right? And the organization is exactly the same as the training data. The first column is going to be gamma for 100 samples. The second column is going to be porosity for 100 samples, and the last column is going to be the manual classification, right? It's classification based upon a human judgment, right? And then this time we are not going to do this kind of vectorized calculation, right? In the previous one-dimensional example, we computed the posterior in just one line of code because we are treating the testing data as just one vector, and then we did a vectorized calculation for the posterior probabilities, right? But here we're gonna sort of do a loop. We're gonna loop through the testing data, and then for each of the rock sample inside of the testing data, we're gonna make a prediction based upon its gamma and porosity values, right? And then we're going to compare our prediction with the manual pick, which is the last column of the testing data, right? So we're going to do a for loop. But before we do the loop, let's come up with a variable that's going to store the total number of incorrect predictions. We're going to call it a miss. We're going to initialize it to 0. And now let's do a for loop, right? We're going to do a tuple unpacking. So G is going to be gamma value, P is going to be porosity value, and then F is going to be the facies classification, manual facies classification, right? And then in testing data, right? The horizontal axis is going to be X, the horizontal, the feature vector. The feature vector is going to be a vector of just gamma and porosity value, right? That's going to be our horizontal axis, right? And this time we're not going to compute the posterior directly. We're going to compute the natural log of the posterior, right? So we're going to compute this formula. So it's going to be like this. It's going to be like this, right? So all we need is this particular term, right? C is a constant. We don't really have to compute it, but we do need to actually compute this matrix vector multiplication, right? And then this subtraction of the natural log of the determinants, right? So how are we going to do that, right? Using the x value for each of the individual testing data, right? So L0, that's the logged posterior for shell, right? Logged posterior, natural logged posterior of the shell, right? It's going to be minus x is a vector, right? Subtract GP0 mean it's also a vector, right? And that's this part, right? But we are going to have to actually do the result of the subtraction is going to be a vector, right? But we are going to have to do a matrix vector multiplication or vector matrix multiplication with the inverse of the covariance matrix. So how do we actually do that, right? In NumPy, the matrix multiplication is called the dot function, and this dot function is kind of misleading, right? Because it looks like you are doing a unit product, but in fact it's not. It's actually doing this kind of vector matrix multiplication, following the rules of matrix multiplication, right? And that's exactly what we want. So GP0, COV, covariance, the inverse, right? And then the result of this multiplication is gonna be another vector, and this vector has to be multiplied with this vector again. So it's another dot, right? It's another dot. X subtract GP0 mean, right? And this whole thing has to be divided by 2. Maybe it's a bad idea to stop there, right? So, but it's okay. It's okay. Let's continue writing it, right? Let's continue writing it. But we are not done yet. We are not done yet. We still need to subtract this one, right? The determinants, the natural log of the determinants, and then divided by 2, right? And then plus the prior. So we're not done yet. So we have to subtract np dot. The natural log of NumPy function is np dot log, and then GP0 COV, the determinant of it, right? And then divided by 2, and then plus np dot log in prior 0, right? So that's the logged likelihood for shell, right? That's the logged posterior of the shell, right? So let's make a copy of it, and then let's paste. Let's compute the corresponding values for sandstone, right? All we have to do is to actually replace the zeros with ones, right? And that's the only modification that we need to actually make. Right. So what's going to be our prediction based upon these two logged posterior, right? So our prediction, we're going to initialize it to 0. So our prediction is going to be, our default prediction is going to be it's a shell, right? It's a shell. But if L1 is larger than L0, then we're going to change the value of prediction to 1, right? So that's these 3 lines of code is going to make sure that the predicted value is computed based upon L0 and L1, right? It's not going to be always 0, right? Because we have this comparison here, this conditional here, right? But making a prediction is not the goal right here, because we need to actually compare the prediction with the manual pick, this f value that's already inside of the testing data, right? So how do we actually do that? Right? So we're going to compute the absolute value of prediction subtract the manual pick f, right? So if this absolute value is larger than 0.1, we're going to increment the count, the error count by 1, right? And then that's it. So now let's close the loop for the testing data, and then print total miss the prediction, and then that's our miss value, right? So we have 100 testing data, right? 100 samples for the testing data. Let's see how. So total missed prediction is actually 0, right? So we didn't actually miss any values for the prediction, right? So this is a good result, right? That's a good result for the predicted for testing data we did. For the testing data which is not exposed to the training process. So for all the training process, we are using only the training data, right? We didn't actually use any of the testing data. But once you apply this best estimates, best posterior to the training data, you get a perfect classification rate, right? And now let's make some plots. Let's try to actually make some plots, right? But now the plots are slightly more difficult to make because it's a two-dimensional plot now, right? So first let's try to actually make some plots of the training data, right? The training data are just the points, right? Training data and testing data. Those data are just the points. So I'm gonna copy over some code. So this is actually plotting the training data, right? So all the shell are gonna be plotted on a horizontal axis, which is porosity, which is the second column of the GP0 array. GP0 array is what? GP0 array is the training data, right? It's only got 2 columns. The first column, the zeroth column is gamma. The first column is going to be porosity, right? So here I'm plotting the horizontal axis as porosity, the vertical axis as gamma, right? And then for shell, it's going to be black circles, and then for sandstone, it's going to be black crosses, right? So and then I'm looking at the testing data here, right? I'm selecting the testing data. So here I'm comparing the last column of the testing data with 0, which means that it's a manual pick is the manual classification is shell, right? I'm storing the ID, the row ID for those for the comparison to be true, and then ID1 is going to be the row ID for the sandstones in the testing data, and then I'm plotting the testing data in red color, right? And for shell it's a circle, and for sandstone it's going to be a cross, right? So if I run this code, I'm supposed to see this kind of two-dimensional plot, right? I'm supposed to see this kind of two-dimensional plot, right? So red is testing data, and then black is training data, right? So what's going to be the posterior, right? What's going to be the posterior? The posterior are going to be two-dimensional Gaussian, right? But this kind of two-dimensional Gaussian has to be visualized. If we are using this kind of a map view, we can visualize the two-dimensional Gaussian as contours. So how do we actually construct those contours, right? So we're going to need some kind of a mesh or two-dimensional grid space for this kind of a gamma porosity axis, right? So we're going to do that by by specifying the minimum and the maximum values. So what we're going to do is to do this thing. Again, I'm going to copy over some codes. Right. So Pmin is going to be the minimum of the porosity of the training data, and then Pmax is going to be the maximum porosity inside of the training data, and then Gmin is the minimum gamma value for the training data, and then Gmax is going to be the maximum training data gamma value in the training data, and then small p is just going to be a horizontal axis that goes from Pmin to Pmax with an interval of 0.001, and then small g is going to be another vertical axis. It's a one-dimensional vertical axis that goes from Gmin to Gmax with an interval of 0.1, right? And then at this point, we can actually construct the two-dimensional axis or two-dimensional mesh. If you have used MATLAB before, this function call is remarkably similar. It's exactly the same function name actually. It's called a mesh grid. This mesh grid function of NumPy is gonna take the two horizontal axes, the two one-dimensional axis, and then construct a two-dimensional mesh from it. So capital G and capital P is gonna be a two-dimensional mesh, right? And then we're gonna use Z0 and Z1 to represent the logged posterior for the two distributions, for the two-dimensional Gaussian distributions, right? And then how do we actually construct it? How do we actually fill up the values? They are initialized to all zeros, right? But how we're gonna sort of get the correct value for them, right? We're gonna do this thing. So it's gonna be a nested loop. We're gonna go through all the different rows and columns, and then for each of the mesh point, we're going to construct a horizontal axis, right? And then the x value, we're going to construct an x value based upon this two-dimensional mesh, and then we're just going to bring this x value into our best estimate posterior or logged posterior, which is these expressions, right? So here the x is going to be grid points, the two-dimensional grid points, right? And then the formula is actually exactly the same, right? So once the Z0 and the Z1 are filled up with the correct values, we can make contour plots. Right? And the command for making the contour plots is just called PLT contour, right? We're gonna make, so the horizontal axis is gonna be the two-dimensional G and P we constructed here, and then Z0 is the two-dimensional matrix here, right? Z1 is the two-dimensional matrix here, and then we're concerned about these four different levels, right? It's gonna do four contours. So now if we run this code, so now it's gonna produce this kind of a contour, right? So again, the dots are actually training, and the dots and crosses are training data and testing data, but the contours were drawn based upon the posterior probability, which is assumed to be Gaussian, right? The logged posterior probability. But now let's look at the FDA analysis, right? Let's look at the discriminative approach, right? What's going to be the decision boundary, right? Again, we have to actually compute this common sigma, right? We have to compute this common sigma. So this common sigma, is going to equal to prior 0 times GP0 COV plus prior 1 times GP1 COV, right? That's the prior weighted summation of the individual covariance matrices, right? And then we have to actually get the inverse now, sigma inverse. This time it's not just a division, right? We really have to actually call the linear algebra linalg dot inverse function to get the inverse, right? And now A is going to equal to what? A is going to equal to the sigma inverse times the subtraction of the two averages, right? But now the averages are going to be two vectors. It's not going to be scalars anymore. So what we have to do is to actually do a matrix we have to do a matrix vector multiplication, right? That's the dot function, and then GP0 mean, that's a vector, subtract another GP1 mean, right? That's another average. So that's A value, right? What's going to be the b value, right? The b value is going to be slightly more complicated, but the formula is exactly identical. We have to worry about the matrix's inverse, right? And then matrix vector multiplications. And then I'm just going to copy the code over. It's almost identical to the one-dimensional case if you account for the inverses and the matrix vector multiplications. Right, that's our b value. Maybe let's try to break it into like multiple lines, right? And then that's the prior. So this term corresponds to the first thing here, right? And then this term corresponds to this term here, right? And then that's the ratio of the priors, right? Log the ratio of the priors. But now you have to sort of be careful about how do you actually solve the equation, right? So it's still A transpose times X, right? But A is a two vector, X is another vector. So it's A1, the first element of A, times X1. X1 is what? X1 is going to be porosity. X1 is going to be porosity, right? And then X2 is going to be gamma, right? So how do we actually get a line that can be actually plotted on this two-dimensional plot, right? So we have to actually separate the A vector into like two elements, A1 and A2, right? A0 and A1 basically. And then we have to actually compute the gamma for every corresponding porosity, right? And let's call this gamma value. Let's call it GA. GA is going to equal to what? It's going to equal to minus the second element in A vector times. We are going to need a horizontal axis in order to actually plot the line. The horizontal axis is going to be a one-dimensional porosity, right? Do we have a one-dimensional porosity? We have it here. That's porosity here, right? A1 times porosity, right? That's our independent variable. And then we have to sort of add B and then divide by A0, right? And once we have GA, we can actually plot this line, right? Right, and then plotting this line just means horizontal axis is P, vertical axis is gamma A, and then let's limit the horizontal and the vertical axis to the corresponding range, right? And now let's run this code. So now this red line is our FDA criterion or critical values for separating porosity and for separating sand and shell, right? So you can sort of see for the testing data, this line is actually pretty good, right? It actually separates sand from shell perfectly, right? But for the training data, the black symbols, we have two samples that are misclassified if we use this FDA criteria, using this FDA determining line, right? But it's okay, it's okay. This kind of misclassification for the training data is not too bad, right? There are of course lots of different ways for improving this kind of results, but for demonstration purposes, that should be sufficient for us to actually look at what the FDA actually does. Right? It's going to draw a line. It's going to draw an optimal line to separate the two different categories. And that's our two-dimensional example.